Hello and welcome to the segment 6. So in this segment we will talk about the fine tuning. So why we need fine tuning we have already discussed, and we have already seen the supervised fine tuning. So in this segment we are almost doing the fine tuning for the entire model, but or all the parameters, but for the memory constrained scenarios. Okay, so you can see here full FT, full fine tuning when we want to do. The frozen is the segment is the base. So all the weights in the base pre-trained model is frozen or fixed. By the way, if you have seen before the transfer learning in the convolutional neural networks, for an example, what we usually do, we set exactly the layers for which we want to train the weights for, and the rest of the layers weights are kept fixed or frozen. How we do that? We do usually with the, yes, so you know how to freeze the model weights. Basically the backward pass should not update the parameters, so gradient should be false, right? Now here in this case we are trying to see that how the parameters are getting fine tuned, right? So the base parameters, which are the pre-trained parameters, are being frozen across the methods that you see here, be it full fine tuning, be it selective, be it LoRA or QLoRA. We will come to these, but the full fine tuning we have already seen, supervised full fine tuning. So there the trainable parameters are the, you can see the sizes. Okay, so the trainable parameters, optimizer state, so all these are basically same size of your frozen base. So basically you have the same size full parameter fine tuning. Now for the selective fine tuning, you can select which are the layers similar to the convolutional neural networks transfer learning you have done, so similar to that. Now in the LoRA, so what PEFT changes, PEFT freezes the backbone and trains only a small set of extra parameters, and that's why it is the PEFT is not updating the original parameters. You are keeping the parameters of the pre-trained model frozen across the different fine tuning methods, that is fine, but what exactly you are training for? Are you training to update? Are you training so this sentence is very, very important to understand. Are you training this, or are you fine tuning or retraining the model to update all the base parameters, or to update few more extra parameters? That is the difference between your PEFT and LoRA. So LoRA actually does train or fine tune the model with less number of parameters to learn, but in the end or eventually we actually update all the parameters in the base model. So now distinction between this full fine tuning and LoRA you have to very, very carefully understand, because you have to apply LoRA or QLoRA or the state of the art fine tuning techniques in the deployments, let's say. Now when we are doing full training, the supervised full training or supervised fine tuning, that time we did not freeze anything. I mean, it's just all the parameters you load, you do the backward pass for these formats, the data that we have new data set, and you do the backward pass and retrain. All the parameters are getting updated. Selective fine tuning says that okay, freeze the few parameters and take few parameters only, new parameters. So basically you add some new parameters into that and train only those parameters to update. That is the PEFT. The PEFT means parameter efficient. So parameter efficiency means here we are not training the entire parameter. So that is the parameter efficiency that you are bringing. But LoRA says that okay, you train few parameters, but in the end you update all the parameters. So this is the difference. Okay, so if the task can be solved with prompts or retrieval, do that first. Again, this is the same way to think about the fine tuning. Okay, so RAG and prompting should be first. Okay, so that is being done, and basically if you need parameter updates, PEFT is usually the first adaptation, because you just add some few parameters and train that and see how it performs. and then you go for full fine tuning, and basically the path is to go with LoRA. Okay, so you can see that the largest savings come from the not training, storing and shipping full pre-task copies of the backbone. Okay. So essentially it's not from training. Okay, so you have to understand the LoRA essentially trains. You can see how many parameters it is getting updating, or it is updating. So this essentially works on a fundamental method to reduce the storage, the memory efficiency. So the savings come from storing and shipping the full pre-task copies to the backbone. So it will update the backbone parameters, the pre-trained parameters, but there is a method. So LoRA preserves the familiar backpropagation workflow while shrinking the trainable state to a small low rank update, and that makes it simple to implement, easy to checkpoint and friendly to deploy also. So for deployment purposes also we usually use LoRA efficiency based fine tuning, and obviously this is the path that we talked about already. So now I told you about the performance efficient fine tuning, or PEFT. So here you are seeing the PEFT adaptation. So you have the transformer layers, right? So what are the transformer layers? You have the multi-head attention, you have the feed forward layer, you have the normalization. In the original transformer layer you do not have the adapter. There is no adapter in the, or adapter layer as such in the base model. So that means you have learned the parameters here, you have learned the parameters here, you have learned the parameters here, here, but these two, let's say this is a layer, a single block, and these two are newly added layer with this feed forward down projection, nonlinearity added to train it backwardly, and then you have the feed forward up projection. So these are the let's say components of your adaptation layer. So that means some weights are involved in this. So essentially I am trying to learn from representation going from here to here how this projection happens for this particular context that I want to learn through this adapter. I do not want to update the weights here, rather I will just update the weights in these two layers. So these are my newly added parameter. So this is called the performance efficient fine tuning. I am not updating all the layers, I am freezing their weights and I am updating the weight values here and here. Okay, so this is efficient because we are not training for the entire layer, but since the amount of the data that needs to be processed into this feed forward projection, down and up projection itself, that will take, or that will be basically the huge number of weights involved in these projections in the adaptation layers itself, but they reduce the overall number of parameters obviously very clearly. LoRA on the other hand, it's a frozen weight plus a trainable low rank update. Okay, it is too expensive to fine tune all parameters in a large model, obviously, that we talked about. Very simple GPT-2, which is very tiny model, it takes around millions of parameters that you have seen, and obviously trillions of parameter, how much big it can be, and if we want to update, it will take even 3 times 4 times more memory to sustain. So during fine tuning we initialize with pre-trained parameters, okay, and the update to buy following the objective of maximum log likelihood of the probability that given set of previous text, the output generation is the probability distribution of this YT. Okay. Okay, so these are very specific mathematics that is working behind it. However, the main component is the component what exactly we learn or what exactly we train for. Okay. So you can see that W0 is the matrix or the weight matrix, that is the fixed, the base model, let's say, okay, base model parameter. So we want to update that, this entire matrix So essentially if I have a matrix of, let's say, 32 by 32, so that means each of these elements should be updated after my fine tuning. That is the target. Now we say that, well, you do not need to train the model with the entire parameter, you keep it fixed, but you train with another set of parameters which is basically your B and A matrix. Now what is B and A? B and A is the low rank or the matrix decomposed values or matrices of this W0. So what is a rank? Rank means what? If you go back to the basics of linear algebra, you will be able to answer that this is basically number of linearly independent rows or columns, let's say columns. Okay. So that means if I have rank 2 for a 5 by 5 matrix, so that means 2 independent column and all the columns can be generated from these 2 independent columns, right? All the other column elements can be generated. So essentially we do not need to represent this matrix, or we do not need all the values to represent 5 by 5 matrix. So if I decompose the matrix, okay, to, let's say, so I had the 5 by 5, so now my matrix is, let's say, 5 by 1 into 1 by 5. So if I have rank 1, then I can decompose it into 2 matrices, 5 by 1 and 1 by 5, where 1 is the rank, and basically if I multiply them, you will get back to the original matrix, and that is the basic fundamental mathematics that is being implemented in LoRA. What it says, so that now you can imagine that W0, which is a very huge matrix, you do not need to use that for learning of the all the parameters, right? So the assumption is you can decompose that the full matrix into 2 sub matrices, which is the low rank matrices, which are, let's say, B and A, and you will learn these B and A values, and in the end you do the matrix multiplication and add to that previous frozen value, which is W0, and you will get the updated weights. So that means you do not need to, so that 5 by 5 matrix, how many matrix elements were there in the complete fine tuning? 25. But if I had broken that into 2 sub matrices, B and A, which is 5 by 1 and 1 by 5, so total how many elements I am training with? 10 elements. You can see that for this simple example, I have reduced the number of parameters by a half, even, I mean less than even half. So 2 times reduction I have done. But in the end, after the training, what I will do? I will matrix multiply or learned weights for B and learned weights for A, and then I will create this W dot or delta W, for which I need to change, make the change, and I will just add it. You get. For practical implementation, you need to obviously tune how much rank you need to apply that, because I do not know which rank will give me the best delta Wx, which is the best value for this, and that is basically the math behind your LoRA. And QLoRA or quantized LoRA is basically the quantized version of this particular thing to reduce the memory or occupation further, optimize. Okay, so applying LoRA to transformer is can be applied any weight matrices in deep learning, but we usually use for specifically to transformers, because the reduction is high. Okay, because if you have very high large matrices, your efficiency or the if you go for reduction, it will be easy to let's say match up the performance also. The benefit is no need to track optimizer state for frozen parameters, smaller checkpoint size for GPT-3 1.2 terabyte of size to store the parameters, which is in the training we will need 350 GB. You can see how much after applying LoRA, how much reduction we can do, and for inference we can even reduce further. Okay, because obviously you do not need to store the activations, gradients and other framework auxiliary values. Now here no additional inference latency and speed up during training also you can achieve. And as I said, QLoRA obviously major innovation was 4-bit normal float, double quantization page optimizer. So there are few specifics. You can go to this paper, basically the QLoRA paper, and try to read about the comparisons also. So this is the LoRa, and basically you can see that the quantized version 4-bit transformer. So from 16-bit transformer to 4-bit transformer. So it reduces the average memory requirement, obviously preserving the performance compared to 16-bit fully fine-tuned baseline. So there are comparisons to see. Yeah, so to give a full view of exactly how this works, so here you can see this complete transformer block. You have the QKV and output. So these are the self attention projections, right? And then you have the attention softmax combination heads from multiple heads combination, and then you have the MLP projections to up. So this is the adapter, and then you have the normalizations, residual connections, and output state. So in this transformer block, you will try to apply all this fine tuning. Okay, so scenarios again, QLoRA style will be target modules are mostly all linears, and typically R values, which is the rank value which is being to be chosen, 16 to 64. Rank value means R. So if you have D by D matrix, which is basically your W0, so D into R, R into D. So that is the decomposition that we want to apply. So R is here, you can choose 8, 16, 32, 64, whatever. For QKB projections, we usually use 8 to 32, that is the usual choices. In the LoRa paper also you can see the increased number of or the different values of R's and how the model performance varies. We will go to the code section also to understand how it performs. Okay. So let us go to the code section. Okay, so the LoRa key equation we already discussed, W0x plus hyperparameter ratio alpha and R, B and A x. So now here you can see that alpha and R for practical implementation or for the deployment purposes, we usually use this ratio where alpha is the scaling factor, usually it's the double the mask value or R value, and R is your rank or the hyperparameter which varies from 4 to 64, we talked about that, and obviously your W0 A B are the matrices. So frozen is the pre-trained weights, your A and B are trained, very basic. Okay. Now for practical implementation, again another tweak is to introduce or induce this A to be trained with initialization from or the values picked from or sampled from Gaussian distribution with values, and B to be start or the initialized with zeros. Okay, so that initially it does not let us say learn noisy representations. Okay, so obviously your A and B multiplication will be 0 in the first go, but that time anyway you will learn for A, and basically you will start for learning from B in the next step, and so on and so forth. So essentially the LoRa, here you can see the R equal to 16 that we have started with, and the initialization values are here 64, 64, 8, D, K and R. Okay. So these are the few random initialization for your A matrix and B matrix. Okay, because you have to have random initialization from the Gaussian distribution, and here you have the or normal distribution, here you have the 0 initialization. And then once you have the initialization, obviously your delta init, delta W init, which is basically the multiplication of these two matrix, right. So this is the delta W which we want to learn, right. So essentially we are learning only the B demo and A demo parameters, and if I just multiply the B or basically your delta W init will be initialized. Okay. Then the parameters, after some training we are just checking, and the merged output. So W merge will be your W0, which is the base parameters which is already frozen, and then alpha by R demo into, now you can actually vary the R demo and see what are the performances that you get, and then the multiplication between these two low rank matrices, and then you can visualize the LoRa structure, and then the parameters are basically these parameters, right. So these are the few settings that you need to do, and you need to consider for LoRa initialization. And you can see that for GPT-2 you have the layer D into K 768 768. So this is your full layer. For LoRa R equal to 16, you have reduction of 24 times in terms of data to be stored or the parameters to be trained for. Okay, and for Llama 70B you have almost 256 times less storage for data. So you can imagine how much efficiency you can get by applying this QLoRA or LoRa basically here. And you can see that this is drawn from this Gaussian distribution. You have maximum value is this, and for this case you have zeros, zero initialization, and delta W is basically your zero initialization. And your after few learning, you can see the 64 by 64, which is basically your frozen weight, and BA, which is returning your delta W, which is 64 by 64, which is the representation that you are seeing here. And here basically is the parameter count with different number of R's. As I said, you can do this implementation by choosing what should be your optimized R value for your specific training data. And for that you can go for a manual LoRa implementation. Again, you have all the library files or packages also to learn with LoRa or to train the models with LoRa. Here we are basically freezing the original layers because requires grad or gradient is false. So you can see how to freeze the model weights. So here we are freezing all the weights. No need to change or no need to use that. Low rank matrices are being initialized. Yeah, so these are the parameters, and then the initialization happens here. And then the forward pass, in the forward pass I have the linear, so basically x. Now you can see that here you have the result plus equal to x at a self dot LoRa AT and basically your self LoRa B. So these are the two matrices, and this is the scaling factor, and you are returning the result for. So now this is the linear LoRa. So you have the count equal to 0 and new layer with the LoRa layer. So this is the main layer that we want to implement or we want to execute, and then we copy the weights and to the original model to make it available. And this is the applying custom LoRa to GPT-2. So the same layers that we have just defined, we can apply it, and basically we can see what is the training values after the complete training. And obviously here you can see that there is a unexpected behavior because of the trainable parameters is 81, and your after LoRa you have the total number of parameters here. This is basically your optimization did not happen properly. So if you replace with let's say more number of layers with LoRa linear, so then you have the parameter reduction properly with the 33% here, and basically the full training size also you can see. So you can just now play with the different parameters, hyperparameters, and the size, the rank values, the scaling factors of all these experiments, and see a number of layers and see how the performance can be improved further, or the data also you can move from one data set to another data set and try to see. So for all your experiments, this Hugging Face community will be very beneficial for you to follow. Obviously you can see the models, so thousands of models are there to try with, and you can see many such models are there which you can change the architecture also. Some architectures are frozen, some architectures you can actually change. So some open architectures are there as well. The data sets, you should look into the data sets that are available for your different tasks. Obviously different documents are there to help you with. So this Hugging Face repository will give you the up-to-date implementations, libraries, packages for all the optimizations that are available for your LLM training, and especially for any algorithm, but usually if you want to optimize fully, you should be able to actually see different learnings or basically the optimization libraries that is already available in this Hugging Face. So you should be able to download them and basically work with them. Okay, so there are a few guides as well. So now you have learned how to fine tune the large language models for specific or domain specific tasks and how to deploy. Obviously inference will follow the training. Okay, so with that we will conclude here, and in agentic AI we will also touch down or pick up on few optimizations and techniques that we have learnt here and apply it in the actual application engineering. Thank you, and see you in the next week.